Hi there, this is lesson 5, charging a capacitor. So first let's look at how, I'm going to recap the equation from last lesson and then I'm going to show you how to rearrange it. So we've got Q equals Q naught e to the minus t over RC. So let's say, for example, we wanted to rearrange to find RC. So first of all, we need to get rid of this E. So we need to do the opposite of E, which is log, natural log. It's the button LN on your calculator. So then we just log everything. So that means we do log Q equals, we've got log Q naught. And what happens, you should be okay with this if you do maths. If not, you would get log Q naught, and then the E just disappears and we're left with minus T over RC. So we're nearly there. So we've got log Q equals log Q naught minus T over RC. You need to get rid of this log Q naught. So let's subtract it on the other side. So we've got log Q minus log Q naught equals minus T over RC. Now it is perfectly viable to just keep this as one thing, and RC would be minus T divided by log Q minus log Q naught. That's fine. You can do that. RC is equal to minus T divided by log Q minus log Q naught. That's okay. If you do maths, you may be looking at the log Q minus log Q naught and thinking, well, the equivalent to log Q minus log Q naught, which I'll just show you here, is log of Q divided by Q naught. So if you want to do that, if you've got some numbers, so you end up with log of a number, that's perfectly fine as well. Either or. When we do something, you can try the examples. If you're not too confident, I will be going through it anyway, and I will be as explicit as possible. Anyway, let's move on. If you need to pause or rewind at any time, please do. So let's have a go at this question. So if you want to pause, they're quite lengthy, these ones, they're quite challenging. So a 680 microfarad capacitor is charged fully from a 12 volt battery. At time t equals 0, the capacitor begins to discharge to a resistor. When t equals 25 seconds, the energy remaining in the capacitor is 1/4 of the energy it stored at 12 volts. So the first thing we're going to do is to determine the PD, or the voltage across the capacitor at t equals 25 seconds. So what we know at 25 seconds is that we have 1/4 of the energy it stored at 12 volts. So the equation would be from lesson 2, energy is equal to 1/2 CV squared. So if we've got 1/4 of the energy, then the voltage must be, the capacitance is constant, so the voltage must be 1/2, because 1/2 squared would be 1/4, which would make both sides equivalent. So half the voltage, so the voltage at 25 seconds would be 12 divided by 2. So that would be 6 volts. So that's A done. Part 1 done. Let's do part 2. So this time we're going to calculate the time constant. So we're dealing with voltage, so we're going to do V equals max voltage E minus T over RC. So we want the time constant, so we want RC. RC is tau, which is the time constant. So the voltage, we figured out earlier, is 6. V naught, the max voltage, is 12. Then we've got E to the minus, it's at 25 seconds, divided by the time constant 10. So we need to rearrange this. So we have to log everything. So it's log 6 equals log 12 minus 25 over 10. So now you could just, do log 6 minus log 12 and then rearrange it. That'd be perfectly fine. Remember though, I said earlier that log 6 minus log 12 would actually be log of 6 over 12. So you could write that as log 6 over 12, which is log of 1/2. So you could write log of 1/2. If you're a proper mathematician, you'll know that log of 1/2 is minus log 2. So you could use log 6 minus log 12 is perfectly fine, by the way. I'm going to use minus log 2. Log 6 minus log 12 is minus log 2. equals minus 25 divided by the time constant. So the time constant is simply 25 divided by log 2. Cancel the negatives. So the time constant is equal to 36.1 seconds. And then the last bit, calculate the resistance of the resistor. So we're going to use time constant is R times C. So that we know the time constant is 36.1 equals the resistor value, which is what we want, multiplied by the capacitance value of 680 times 10 to the minus 6. So 36.1 divided by 680 times 10 to the minus 6 will give you a resistor value of 53 kilo ohms. Hopefully that's okay. Let's move on to the next one. So another tricky one. If you want to pause and have a go. So a charged capacitor of capacitance 50 microfarads is connected across the terminals of a voltmeter of resistance 200 kiloohms. When time t equals 0, the reading on the voltmeter is 20 volts. Calculate the initial charge on the capacitor. So we're going to do Q equals VC. So the voltage is 20 multiplied by the capacitance of 50 times 10 to the minus 6. And 20 times 50 times 10 to the minus 6 is 1 times 10 to the minus 3 coulombs, or 1 millicoulomb. Pretty straightforward. Now we're going to do number 2, calculate the voltage across the capacitor after 20 seconds. So for part 2, it's V equals V naught E minus T over RC. So we're going to need the time constant RC. So time constant RC is 50 times 10 to the minus 6 multiplied by 200 times 10 to the 3. And that gives us 10 seconds. So let's find the voltage. So the voltage is equal to, we've got V naught, max voltage, is 20. Multiplied by E to the power of minus T, which is 20. So we've got minus 20 over 10. So you put that in your calculator. So we've got 20 multiplied by E to the minus 2. That gives us a voltage of 2.71 volts. Not too bad, that one. Part 3, a bit more challenging. Let's have a look. So tricky, this one. So it says the time which must elapse from t equals 0 before 75% of the energy has been dissipated. So that means gone. So how much energy is remaining? Well, it's a quarter. So what we need to do is figure out how much voltage we've got if we've got a quarter of the remaining energy, which we actually looked at in the previous question. So some of you might realise already that the voltage will be half. But energy is equal to half CV squared. And we've got a quarter of energy remaining because 75% has dissipated. And a quarter of the energy is half of the voltage because a half squared is the quarter which is required. So the voltage is half of the initial 20, which is 10. So 20 divided by 2 gives us the 10 volts. So now we can use V equals V naught. E minus T over RC. So I'm going to clear this. We've got the voltage, 10 volts. So we've got V equals V naught, E minus T over RC. So the voltage is 10 equals the maximum voltage, 20. E to the minus T, which we're looking for, divided by the time constant RC, which we calculated to be 10. So then we just need to rearrange. We need to do log 10 equals log 20 minus T over 10. And this time I'm just going to do log 10 minus log 20, which of course is log 10 over 20. But log 10 minus log 20, and then multiply through by 10 to give minus time. If you pop this into your calculator, so you could have, log of, if you did log 10 over 20, that would give you minus log 2. If you're not very good at maths, or you've not done this yet, don't worry about that bit. These two, if you want to check actually this top one, this one, and compare it to this one, you'll get the same answer. Equals minus t, and the time that you will get is 6.93 seconds. So a challenging question, challenging with question 3 with the wording. If you got that right, well done. Let's move on. So the charging equation. So if you're charging a capacitor, the equation is as follows. So we've got charge is equal to the maximum charge. Then we've got brackets. We've got 1 minus e to the minus t over rc. So essentially, whatever number you would normally get doing e to the minus t over rc, you have to do 1 subtract that. So say you've got a 0.3, you would have to do 1 minus 0.3, which would essentially just give 70% of the remaining charge, if that makes sense. So what we'll do is a rather challenging question using this. There's also the one for, we can use it for voltage as well. So V would equal V0. We've got the brackets, 1 minus e to the minus t over rc. Can bracket that. There we have it. So I've got a challenging question for you to go out, then I'm going to give you a little bit more information, and then I'll show you how to do the question. So let's move on. So here we go. Let's pause and have a go. A 2000 microfarad capacitor is charged in bold, through a 1 kilo ohm resistor using a 6 volt supply. So it wants you to calculate the charging current after 2.5 seconds. So here's the trick. A charging current, if you used I equals I0 and then did 1 minus e to the minus t over rc, you'll be wrong. Massively wrong. Because if you remember, the graph for charging current looks like this. The same as discharging. So this equation that I've written at the top does not exist. So let's have a look. Hopefully that didn't catch you, you didn't get caught out by that anyway. So we need the initial current. So we're going to use current is voltage divided by resistance. So the voltage is 6 divided by the resistance of a kilo ohm, so 1000. And 6 divided by 1000 is 6 times 10 to the minus 3 amps, or 6 milliamps. So charging current would just be current is equal to I0 e to the minus t over rc. RC we can calculate, we've just got 2000 microfarads. So let's get the time constant. So we've got the 2000 microfarads, 2000 times 10 to the minus 6, multiplied by 1000 ohms. So we've got the time constant to be 2 seconds. So now let's calculate current. So current is equal to the max current, which we got to be 6 milliamps, multiplied by E to the minus T, which we've got as 2.5 seconds, divided by the time constant of 2 seconds. So if you put that in your calculator, you will get a charging current of 1.72 milliamps. Hopefully that didn't catch you out. If you got that right, well done. Now let's finish off with the charge on the plate after 2.5 seconds. Remembering that the time constant is 2 seconds. So the charge on the plate. Now charge will satisfy this equation. So charge is equal to the maximum charge, brackets, 1 minus e to the minus t over rc. You can bracket this one as well. And then close it off. So let's put some numbers in. Oh, we also need the maximum charge. Remember, charge is voltage times current. Voltage times charge, sorry, C. So voltage is 6 multiplied by the capacitance of 2000 times 10 to the minus 6. So that gives a maximum charge of 0.012 coulombs. So now let's use this equation. So charge is equal to max charge 0.012 brackets 1 minus e to the minus t, so it's minus 2.5 divided by the time constant of 2. And if you put that in your calculator, that will give you a charge that is equal to 8.56 times 10 to the minus 3, or 8.56 millicoulombs. Hopefully that went okay, and your understanding is better now. Thanks for watching. I'll speak to you soon. Thank you.